So I'm going to be talking about a basic talk about explainability that goes all over the place within different models. So first of all, this is not just my research. This is joint with a whole team of more than 15 engineers and researchers across various global labs in India, Argentina, here in New York. Actually, this is live from New Jersey because I'm speaking from my home. Our office is in New York, so welcome to my home. So let's get in because I'm sure everyone's also hungry over there. So the agenda for this talk, first I'm going to talk about why we care about explainability in AI. A lot of this has been covered today, so I will repeat some stuff in that part from Gal, from Irad. And then I'm going to talk about types and methods for explainable AI and divide up the types of tools and where they should be applied. I'll do a deep dive on two tools that are specific in the toolkit that we have, one based on contrastive explanations, which ties very well to the beginning of Gal's talk from the morning, I guess the afternoon there, and then about something in global explanations that we called ProfWeight. And then I'll give a tutorial, if we have time, about how to use the actual tool and show some screenshots on GitHub to show what you can actually do at home yourself. So why do we care about AI? It's been already talked, Irad went through a bunch of these examples, that it's not just used inside the computer science lab anymore. It's used across all industries, all over the place. In credit, to say if a person's to be approved a loan, in employment to target which employees might be considering to leave. In admission tasks, universities want to target certain applicants that they find desirable. In sentencing, people, they're using it for parole guidelines and recommendations. Sorry. So what does it take to trust the decision made by a machine? So in machine learning, a lot of times we would train models and say, get as good accuracy as we can. And we say, well, I have a model that's 99% accurate, but in order to get someone to actually use your model, that's not enough. So we ask two main questions. One, is the model fair? People want to know, is it appropriate to use? And the other question, why did it make this decision? So the fairness is a very important topic, but for this talk, I'm going to be focusing on the other question, asking why did the model make the decision it made? That's what we're going to call explainability. For fairness, there's actually another toolkit that people in the IBM organization made last year as well. So it's no secret that lots of people are interested in AI, in explainable AI. It's been all over the news for a few years now. Good and bad news, ranging across all companies from Amazon, Facebook, us at IBM, Apple very recently. One of the more interesting ones I'll point out here is the article, When a Computer Program Keeps You in Jail. So this was an article about someone who was denied parole, and they actually used the software to give him a score on whether he should be paroled. He got a high score, he wasn't given parole. 2 years in, he had people doing research figuring out why. They found actually that one of the inputs to the system for him specifically was not correct. However, there was no way of knowing what the weight for this feature was, so they said they don't know how much it would have affected the results, so it didn't change anything with his parole. These systems are closely held secrets to a company that privately owns this piece of software. So they're not just going to say how the software works and let people look at their code. There is no way to get explainability for tools like that, and that's just a very important example of how important it is that we develop these algorithms with explainability, because it really affects people's lives here. So when we ask for explainability, this question has been asked and somewhat answered, even a few years ago when they came out with the GDPR, which has also been mentioned today. So it's saying that people have certain rights. One of those things is the right to be provided with meaningful information. But the guidelines, it's still, what does meaningful mean? So we can have lots of discussion on that. One way we can talk about what is meaningful is to say that someone looks at the model and the human can go right along and say, why did the model give that decision? For example, decision tree. So we say that's interpretable. It's easy to understand. Of course, you can argue we can make the decision really hard, really big, and then a human can't parse it so easily. But for a neural network, that's really what we call not interpretable. It's a real black box that we can't say why this decision was made exactly. So we know why explainable AI is so important, and what are some uses of explainable AI? So I'll go through a few of those. One is simplification. So here we have a big neural network. The task is to predict whether or not a piece of code is malware or not. So it does its job well, and then people do some analysis and find out the neural network is really just predicting if this piece of code has comments, because evidently people that write malware don't really like to care to comment their code. So then that poses the question, do we really need a complicated neural network to classify whether a code has comments or not? So such explanations could help in simplifications of models. Debugging. So you have plenty of people interested in self-driving cars now, and take the situation where the self-driving car slows down but doesn't stop at the red light. You need an explanation, why did that happen, so you can debug the system. To find existence of confounders. So here's an example. You have a model that says pneumonia is indicative of not having diabetes. And without having an explanation, there's no reason to know that that's a spurious correlation. Because what if I told you that people with pneumonia are often in the hospital, and when you get admitted to the hospital, by default, you're checked if you have diabetes or not, and most people don't have diabetes. So if you have the marker, a variable also, it says whether or not you were checked for diabetes, that would help get rid of such spurious correlations. To enhance the performance of models. So you have plenty of models that if they give you the results and we could understand them, an expert like a doctor could give some feedback to the machine and we could improve the results of the algorithm, get better accuracy of the algorithm. Fairness, that's been a lot in the news the last year or two, specifically facial recognition software, and plenty of issues on systems that were deemed unfair for particular populations. So getting explanations from those models would help to give a sense of fairness there. We saw this example earlier with the husky in the snow, and the question here, I'm calling it robustness, is to say we need explanations to say, did the system actually say this is a husky because of features of the wolf itself, or because it found the snow and said anything in the snow would be a husky? And so all these things, basically explanations in general, we want people to use our AI tools that we're developing, so it would help with widespread adoption in general. Okay, so now we're going to talk about types and methods. So if there's any message that I can ask you to take from this talk today, it's that one explanation does not fit all. It's the title of the talk. And the reason we say that is because when you talk about explainability, there are many different stakeholders. Everyone's interested in something else. There's no one explanation type for all different models. We've heard many different types of explanations today, different methods, and one thing I think is fair to say is that each method has some value. No method's the best. Everything offers some type of information to the user to understand the model. So if you're the end user, for example, you ask different questions. If you're a doctor using software that told you why someone should get a treatment, you're going to ask the software, why did you recommend this treatment? If you're an affected user, you're someone who was denied a loan by a piece of software, you're asking, why was my loan denied? What can I change so that I can be approved later? If you're a regulatory body, you're asking a system to prove that it's not discriminating. If you're the developer of this AI software, you're asking, is the system performing well? What can I do to improve the system? So depending on who you are, which stakeholder you are, you're asking different questions, and for those different questions, we need different tools. So our toolkit, we released it last summer. It's called AX360. It's on GitHub. And basically these are different dimensions across the top: data explanations, direct interpretability, local, post hoc. So I'll go over all these. The point here is just to say this is a non-exhaustive list. Different companies, everyone's interested in releasing different toolkits. One of the reasons that I would sell on our toolkit is that we really worked hard on giving a lot of demos and tutorials and documentation on how to use the toolkit. And hopefully one of the ways I would judge the success of such toolkits is that we want people to be entering in their own explainability tools. Right now, in the beginning, we just included all IBM homegrown tools. I think there was initially 8 tools. A few months ago, we also included Lime and Shap, so now it's not just our own tools, but the more that will be show how successful it is and that people will use it. So the different dimensions of explainability that I want to talk about: direct interpretability versus post hoc interpretability. So if you're someone that you just need the model to be explainable by itself, we call that direct interpretability. So you want a decision rule or a tree, something simple that you can look at the whole model. Post hoc interpretability is for cases we say when what you're using is a black box, a neural network, and you want interpretability of that. So you might probe it in some way, use some local approximations of it. And another dimension we can talk about explainability is whether you're asking about global or local explanations. So global, you're asking to see the entire predictive model. Local explanations is when you're looking at particular instances. You're asking, why did the model say something about this particular instance? Then we also have static dimension, which is you're just presenting the interpretation as is to the user versus interactive interpretations where the user can interact with some visual display. Right now in our toolkit, we've only focused on static. So this is the taxonomy that's mentioned in the title of the talk. And so this just gives an outline of where all our tools apply, and whenever someone makes a new tool, we should be able to fit it in somewhere here. So if we look at all the static tools, we can say, are we looking for explanations of data or explanations of a model? If you're looking for explanations of a data, we can look at also different dimensions there: samples or features. Samples, if we want to give an explanation, say something about a sample by looking at other samples in the training data, we have a tool called Protodash. Or if you have an unsupervised problem and you need to learn meaningful features, this DIP-VAE tool is about learning disentangled representations. So if anything that you don't have features in the data set, we can still learn features to do something with. If we look at the model side, then we have local versus global explanations. On the local side, we have mostly it's about post hoc. So we have a complex model that we want to say something about, and we can do that with samples of the training data or features directly. And for that, we have the contrastive explanations that I'll talk about. Global, you're looking at the whole model, so you probably want something like trees. In the direct, we have Boolean rules, BRCGs. So this stands for Boolean rules with column generation. This is one of the tools implemented in AIX. And for post hoc, we have surrogate methods such as were mentioned earlier today that you use surrogate methods. We have a specific one that I'll talk about called profweight. So let's dig in deeper to these. So if we are talking about direct global interpretability, we want decision trees or ruleless. So again, we've seen decision trees, ruleless. The longer they get, suddenly it's a little harder for a human to understand. So there has to be some medium met there. Within AIX 360, under direct global interpretability, we have these Boolean decision rules via column generation. So what that is are decision rules that are in DNF form. They're ors of and. So you have a rule that says predict Y if A and B and C, or D and E and F, and so forth. So a variant of this actually won the NeurIPS 2018 FICO challenge that was about predicting loans. And so this is in the tool. This is for Boolean decision rules. There's another one using logistic classifiers. So instead of getting actual rules that are ors of ands, it's doing a logistic classification, giving weights and getting interpretability from the weights. Okay, so that was there. Sorry, that was the direct. Now we're talking about post hoc interpretability. So here we can start with the black box, for example, a neural net, and we want to probe it. So you can probe it with decision trees, with some other simple curves, with a simple neural network. I believe we actually saw this figure for the ensembles in the previous talk, but the idea is you can use such things to get interpretability of a neural network. Another thing in the global scale is, can I take a simple model that if you have a user they're focused on using their simple model, they're not going to use a complicated model, can you transfer information from a complicated model like a neural network to improve the simple model? So you already have a model that's interpretable, that you can get explanations from, but it doesn't do as well as the other model, but people aren't going to use the complicated model. Can you use it to improve the simple model? So there's two types of methods for doing that to mention. One is called knowledge distillation. So this was made in 2015 by Hinton. And the idea there is to distill knowledge from one neural network to the other. Basically, you have one neural network, you pass your training data through it, and use the predictions from that neural network as soft targets for the other neural network. So rather than train the second neural network to the hard targets, the actual labels on the training data, you're going to train it and fit it to the predictions from the first neural network. And this works well for transferring information from one neural network to another of similar complexity. But when we want to transfer from a neural network to a very simple model, we were looking at other methods that we found to do better. And the idea there is to do weighting schemes. So we take predictions from the complex neural network and we use that as some confidence measure to weight the examples and retrain the simple models. And I'll get more into that later. So that was about post hoc global interpretability. Now we have post hoc local interpretability. So one of the common ones when you're looking at image recognition tasks is called saliency maps. So the idea here is to take the gradient of the model with respect to the inputs. So it's saying essentially which inputs do you change a lot that are going to have biggest effect on changing the output of the model. So look at the boat. This is predicted a boat, and the saliency map on the bottom is black and white image, is mostly focusing the white on the boat because those are the pixels that are most likely, if you change those pixels, are going to have biggest effect on the classification of that image. So that's one local method. And the other local method to mention are contrastive explanations, which I'm going to get into next. So CEM stands for contrastive explanation methods. Just going to make sure on the WhatsApp. Okay. So this ties very well into what Gal was talking about this morning. So if you remember the example, it was the first part of his talk, and it was about image captioning. I'm not going to talk about image captioning, but you had a yellow bird, and we're trying to give a caption to that yellow bird, and said, well, this is a yellow bird with a bird with a yellow belly. And a better way to say what that was, this is a bird. This is whatever type of bird, because if it has a yellow belly, but if it also had black stripes, it would be a different class. So this is, there he was talking about it as you have your target, and that would be the discriminator. So I'm going to use slightly different terminology for that. So this is a quote by Tim Miller, and it says, explanations are contrastive. They are sought in response to particular counterfactual cases. That is, people do not ask why event P happened, but rather why event P happened instead of some event Q. So the event Q there was that the bird has black stripes on it. And the real key here, when we're talking about explanations, this was based on a survey of 250 publications from different social science venues. That's the biggest study that we've seen, that this guy is saying people really, the way humans understand things is not by looking at why this happened, but comparing it to something else. And that's why we want to look at contrastive explanations. So I'm going to explain this through the example of looking at whether or not a model says if someone has the cold or the flu. It's a good example because things that are very rare for cold are very common for the flu. And when we talk about contrastive explanations, I'm going to talk about two different types of explanations. One is going to be called the pertinent positive. One will be called the pertinent negative. And so the way we're going to look at it, we're going to look at this patient, and we're going to have a model that says what he has, and the 5 attributes are whether or not he has chills, a stuffy nose, sore throat, headache, or fever. So we're going to look at a patient who's diagnosed with a cold. So the model, you feed in his input. As input, it says this is a patient who has only a stuffy nose and a sore throat. He doesn't have the other 3 features, and the model predicts he is diagnosed with a cold. So we want an explanation. Why does the model say that he was diagnosed with a cold? So the pertinent positive explanation. This is defined as the minimal set of features that he has, such that the model would still predict he has a cold. So we want to look, he only had, before he had a stuffy nose and a sore throat. So this pertinent positive explanation says if he only had a stuffy nose, he would still be predicted to have a cold. So the explanation here says, why is this person with a stuffy nose and sore throat predicted to have a cold? Because if he only had a stuffy nose, he would still be predicted to have a cold. Now, like I said before, every explanation has some type of value. No explanation is best. This is one piece of information that can help a lot. Knowing if the model only had this, then it would predict the same thing. And there's other uses for it. It can also help with debugging a model, because if a model is predicting something using very irrelevant piece of information, it's good to know that to debug the model. So this is pertinent positive. Then we're going to go to the pertinent negative explanation, which from what we've seen so far, humans like actually a lot more. So the pertinent negative explanation is defined as the minimal set of additions that I make to this patient, such that if I add these, he's going to change to a different class. So I want to be able to change his class from cold to flu with the minimal set of additions. So we already had stuffy nose and sore throat. The minimal addition here is a fever. So now the pertinent negative explanation is a patient who has stuffy nose, sore throat, and a fever, and now he has the flu. So the pertinent negative explanation you might say to a user is, why did the model say that this guy with a stuffy nose and a sore throat has a cold? Because if he also had a fever, he would have predicted to have the flu. That's what the pertinent negative explanation is. And that's the type of explanation when people think about things, that's just how people often think, as demonstrated by Tim Miller in his paper. And so this is giving the contrastive explanation method that we've developed is basically outputting these two types of explanations for something, the pertinent positive explanation, the pertinent negative explanation. So we can look at this mathematically. How do we actually learn these? So here's for the pertinent positive explanation, again, the minimal set of features, minimally sufficient set of features such that the original classification is maintained. So we're minimizing over delta. Delta are data points that line the intersection of the original data point, which is XO, and the feature space. So the first term there in the top line, this is saying that the prediction of the new data point delta has to remain the same. So the original prediction was T naught. So the max prediction that is not T naught has to be greater, should be, the max prediction that is not T naught will be less than the prediction of T naught on delta in order for it to remain the same. And we do this, we add some confidence kappa for that. The second line, the regularizations, we want a sparse set of features to learn. So we have L1 penalty on delta. And we also have this extra regularization at the end with this autoencoder. And the idea here is that when you look at which set of features denote the pertinent positive, you want that data point that you've learned, that minimal set of features, to actually be a real data point. You don't want to just select any set of features. So we actually pass this through an autoencoder that we learn on the data set, and we use this regularization to make sure that the new data point is something actually generated within this data set. We've done it without this autoencoder, and using this regularization just gives much smoother explanations. Then we have the pertinent negative. So the pertinent negative is a new data point with minimally necessary additions, such that the original classification is changed. So now we're optimizing over delta, which are the additions. So the new data point that you're going to learn is x naught plus delta. And in the first term, we flipped the two terms because now we want to change the prediction. So we want the new prediction to be greater than the prediction of t naught. And then all the regularizations on the next line are the same. It's just what the objective that we want to change it. That's what's changing here. And both of these formulations are learned through gradient optimization. So then here's some examples of what it actually looks like. So this is on MNIST, a handwritten digit data set. Very commonly used, but not the most interesting, so I'll show others. But easy to show how this works. So the first one is predicted a 3 in the upper left. And then if we look the next box over, the CMPP, this is the pertinent positive. So if you can see on the screen, there's highlighted within that digit, within the white pixels, there's in cyan bluish color. That's a very clear 3. So it's saying the pertinent positive, if only those pixels were illuminated, this would still be predicted a 3. So maybe that's what the model is looking at. This is one type of explanation. And the reason it's a clear 3, what helps there is that addition of the regularization with the autoencoder. The pertinent negative says that if I added that magenta line, that purplish magenta line, then this would have been predicted a 5 instead of a 3. That's why it was predicted a 3, because it doesn't have that extra line that would have changed it to a 5. Then there's other methods, LRP, line that we've heard about today. All these types of explanations give different types of information on why a classifier does what it does. None is the best, though what's nice about the pertinent negative explanation, it gives the humans a direct explanation that says why something happened. The other, even PP, for the pertinent positives, as well as for LRP and line, for image data sets specifically, requires a human to intervene afterwards and look at the image and understand what the explanation is saying. So more interesting example, this is on a procurement fraud data set. So you have these invoices from companies, and we're trying to figure out which invoices are fraudulent. They're each labeled with a risk, low, medium, or high, and there's different events. All the events are listed on the right. So I'll just talk about the high risk one at the bottom. So for out of interest, we look at the pertinent negatives. So this would have been, the pertinent negatives are 2 and 9. So 2 says the vendor is registered with a large corporation. 9 says the vendor has a Dun and Bradstreet number. They didn't have these events, the original invoice. So what it's saying is, if the invoice also had a vendor that was registered as a large corporation and had this Dun and Bradstreet number, it wouldn't have been predicted to be highly fraudulent. And we passed this to experts also, and they agreed. So for that exact one, for example, they say if it had those, it would have been indicative of a much lower risk. And we can make similar comments for the other examples. It's discussed in the paper about this tool as well. Okay, so let me talk about one issue with everything about contrastive explanations that I just said, and that's what are additions. So for black and white images, it's easy to define what is an addition. You take a black pixel, you make it white. That's turning it on. So that's how you can add things. That's how the magenta there, it's just black pixels that we turned white. That made the 3 to a 5. For binary data, it's easy. Flip a feature from 0 to 1, you turned it on. But what does an addition mean for complex data like colored images? You look at something in RGB space, you can't just, there's no concept of turning a part of the image on. So what do we mean by additions that we want to do for generating pertinent negatives? So the solution we came up with was defining addition is adding some either known attributes or learned attributes for the data. So we're going to add attributes rather than turn something on. So if you think of a face, an attribute you can add, you add makeup to the face. That's an attribute you can add. You added a pointy nose, or you added high cheekbones to the face. These are attributes that you can add to the face. Okay, so this is what we called contrastive explanation method with monotonic attribute functions. So one of the inputs now, before we didn't need this. For black and white images, it's easy. There's no attributes, you know, black or white. So now we require the data set to come with attribute functions. So the GI here, these are classifiers. So GI of delta, delta is an image, for example, and GI of delta is a classifier on the ith attribute. So it's saying if delta has the ith attribute or not. So we're optimizing over delta here, and the difference here is in the top line. So now for pertinent positives, we want to make sure that we don't add any new features because we just want a subset of the features. So that's what this first penalty is saying, that all of the classifiers, we're not going to turn any of the ones that are on, any of the ones that are not on for XO, we're not going to turn anything new on. Then we have the sparsity penalty, the binary mask. This is saying we want a sparse set of features for the pertinent positive. And then the last line is the same thing from the basic CEM that I showed you before, that you want to keep the classification. So for pertinent negative, it's somewhat similar, except here we don't want to let anything, we don't want to let any of the features go away. We only want to add things. So we flip the things in the first term. And also here we've added a generator. So for the pertinent positives, it was easy with there we were working for images with superpixels. And so we're just removing superpixels and using a mask. Now, for pertinent negatives, we want to generate new data points, or we want to generate new images, for example. So here we're going to require that we have a generator. And so we're going to pass the delta, the latent variable for our new image through a generator and generate a nice new image, hopefully. The sparsity penalty here, again, is on now the number of attributes that we're going to add. So for the pertinent negative, we want the minimally sufficient number of features added to change the prediction. Changing the prediction is what the second line there is. And then the last line is saying that the new image is, after we pass it through the generator, is close to the original image. And then also in the latent space, the image is very similar to the latent space of the original image. So yes, one kick here is that we are requiring knowing what the latent representation of the data point looks like. So here we have an example, two examples. One is on Celebi, this facial data set. So we came up with our own classes based on the features. So key thing here, this data set is given attributes. So it has the given attributes: high cheekbones, narrow eyes, oval face, bags under eyes, so forth. And what we're predicting is age, sex, and whether or not someone is smiling. So for this first person at the top there, the model is, again, we're feeding a model. We want to add it. We're asking explanation about a model. Why does a model say something about this particular image? So we trained the model, and the model says this is a young male and he's smiling. So the pertinent negative class that it learned, the nearest class with the change is that this is an old female who is not smiling. And the explanation is that if I added brown hair, makeup, and bangs to the young male who's smiling, he would have predicted an old female smiling. So that text, that textual explanation is what makes this so appealing to people, that they can just, we tell them it's easy for any human to understand. Because we use the generator, it's also nice that we do come up with this picture to go with the textual explanation. So you see this looks like a very realistic person. It's added bangs. Those are the pieces of hair that go down the forehead. It's clearly a woman with makeup now. It changed it from young to old. So again, we're asking explanation for a particular model. Whether or not that model is great or not, that's irrelevant. we're asking why did the model do what it's doing. If the model makes bad decisions, I'm still asking why did the model make this bad decision. Then we can look, there's other explanation types. The pertinent positives don't always work well, so which also lends to ask, what is the model actually doing if it's using just those features to make the decision. Line, GradCam is another good tool for looking at visual tasks. So all of these give different types of value. Also mentioned the application on the right. This is from a skin lesion data set. So the top picture is predicted as a melanoma, and the pertinent negative is saying, why is this a melanoma? Because if the melanoma was rounder, it would have been predicted as a nevus. And so the pertinent negative, this is slightly rounder than the original image, which is the melanoma. And in fact, melanomas are known to be very asymmetric. So a key thing here also, sorry, before I move on, for the lesions data set, this did not come with any features. We had to use that DIP-VAE tool that I mentioned before for learning disentangled representations. So we learned attributes on this lesion data set. And then those attributes, it does require a human to go through them and look, what are these attributes telling? So we found features that were indicative of size increasing, going from oval to more round, from light to dark, and saying things about the border definitions. But once the human does that pre-processing step, this explanation tool can be used to explain any other instance on this model without much effort. Okay, so now let's look at another deep dive into another tool, which is called ProfWeight. Okay, so this is about talking about interpretability of something, a new way of thinking of interpretability. Sometimes it's hard to say if someone's interpretable or not, but it's much easier to say a concept of relative interpretability. So is this person interpretable relative to something? So in the student-teacher paradigm, is a teacher interpretable? The way to actually measure if he's interpretable is to give a student their statistics test. Then we get their score. The teacher gives them a lesson. They take another test. Did they do better on this subject? And that's how we tell, is the teacher interpretable relative to that student? If they improved, they're interpretable with respect to the student. If the student doesn't do well, they are not interpretable relative to that student. And this is a very well known notion for humans. And our point is that we can apply this to models as well. So this whole question, neural networks are not interpretable, but what if we thought about it in a different way and said, well, is there a way to define neural networks as interpretable relative to some other model? If I can transfer information from a neural network to a decision tree and improve the performance of that decision tree, maybe it is interpretable in some sense. So again, this is just saying that we want relative interpretability now, and interpretability isn't just about the humans anymore. It's about what that guy in the middle here is doing, who's severely beating the other two guys. So a real use case, not MNIST, for using this type of tool. We have fabrication engineers, and they need to measure the amount of metal etched on manufactured wafers. So the point here is that they're using decision trees, and they've been using them for years. They understand how to get insight from these tools, and they're not going to change what they're using. Even though we come up with a neural network that has great performance, better than their decision tree, they're not going to use the neural network. But how can I use the neural network to still help them out? So at the top, this is what they do. They use training data, they train their decision tree. What we want to do is use the training data, we pass it through the neural network that does really well, and we're going to use that to give them a decision tree, a different one than they had, but that does better than what they had. So same complexity, they're going to be happy with it, they can still get their insights. And so how do we actually transfer information? So one way we do that, when we talk about neural networks in particular, what we did was take the neural network and we attach probes to each layer. So what these probes are essentially are logistic classifiers. We want to measure at each layer how much information is already learned up to that point? Do we actually need more layers? So we fix the neural network, and we train just the weights and the logistic classifiers at each layer. And then what we're going to do is create these confidence profiles. Confidence profile is basically giving some measure of whether an example is easy or hard. So for example, the easy example there, that's a 7. After only one layer, it's already easy to predict. However, for the hard example, we look at the profile at the first probe, at the second probe, it's still hard to predict. So using these profiles, what the information we can pass from the complex model, the neural network, to a simple model is saying whether this instance is hard or not. Should you focus, this model isn't as smart as me, so don't bother wasting your time on this example. So the general problem we look at for this is creating weights that are functions of the first two probes. Oops, sorry, I have something in the middle of my screen. Okay, so yeah, so we are creating weights that are functions of the first two probes, and the question is, so we're going to take these weights and we're going to retrain the simple model. We're going to use the weights on each data point, pass the data point I through this, get the weight of I, and put that weight on the ith point when you train the simple model. Our initial method is taking f to either be the output of the model, which here is like saying use w equals probe 2, or also using the average of the probes to give more a measure of the overall complexity, difficulty of the data point. So that was an easier way to just define what is the function of the probes. Another idea, you could learn what that function is. So we don't know what function. Should you use the average? We don't know. So we can say we're going to learn this through an optimization problem. Lambda here is the loss function. SW beta is the simple model parameterized by beta, and the weights W used to train that new model that's parameterized by beta are going to be optimized over class C. This class C can be neural networks. So those weights are neural networks that take as input the probes. And we're going to learn that neural network, which is the function of the probes. And we can do that using alternating minimization. One problem with that, you think of it, the weights easily, you minimize that, everything's positive, so just take all the weights, we can go to 0, so we need a regularization. The regularization we add here is basically saying that the expected weight equals 1. And so we have some theory to suggest why we want to do that. And the theory is essentially saying that taking this as the constraint makes what we're doing importance sampling, and doing importance sampling using this type of weight. So you see in the theorem the ratio there, p of x given y divided by p of m of x given y. So the p is just the test data, m is the classifier from the training data that we have. But if we use this type of importance sampling at the bottom, what we see is essentially on the right-hand side of equation 2 down there, we have this is essentially the Bayes optimal classifier error of using on the original test distribution, which we don't know. So it's saying using this constraint gives us the optimal Bayes classifier. So that's motivation on why we want to use this regularization. And actually using that regularization gives good performance. So here's the performance on that initial use case with the fabrication engineers. So the complex model we use there is a 6-layer neural network. They're very fixated on using the decision tree. What they're using is CART. The standard is the performance of their initial decision tree. And the two prof weights are using our information transfer, which the first one is learning neural networks, so we're learning the function of the probes, and the second one with the AUC is taking an average of the probes. So here learning doesn't do any better, but the point is we can get a lot of improvement by transferring from the complex model to a decision tree. There's a 13% improvement. You have a simple decision tree without any weighting. This is how it does. We just learn weights for it, and we can do much better. A point to say that using all the entire confidence profile is important. Conf weight here is just using the prediction of the final model as the function. So using all the intermediate layers does give a lot of improvement. And the last insight I'm going to give from using this information transfer that I thought is pretty neat is that what we learn is the smartest teacher is not always the best teacher. So here we have, we do information transfer from different complex models of decreasing complexity. So on the bottom, from left to right, the CMs are in decreasing complexity, and we transfer to a target model on the top. And as we see, the error goes down. TM4 has the lowest errors. So transferring from CM4 actually does better. CM1 is the smartest, quote unquote, complex model to transfer from, but even though it's the best model, it's not as good at transferring information. It's not all smart teachers, all smart people are great at teaching, at letting their students know what they're thinking. And I thought that's a pretty neat insight from this information transfer tool. Okay, so how much time do I have? A few minutes to go over quickly through this tutorial. So the AIX 360, it's on GitHub. It's open source library. As I said, one of the things we like about it and hope people will like is that it has lots of tutorials and notebooks. If you look at it, there's a bunch of directories, and if you just want to use it at home, I recommend going to the examples to get an idea of how to use it. There's all these different tools that I've shown you today. And so I will show you two tools very quickly. One is the contrastive explanations. Now, as I said before, you can run these contrastive explanations on data sets that do or do not have features that come with them. However, if they don't, you do have to learn them. So as far as this tool goes, you do have to have predefined high-level attributes. You have to have classifiers on them to use the tool. So the example, we have a bunch of import statements. All the tutorials here show you how to download data, has all the references to the papers for you. So for this one, we need a TensorFlow session. We load the model because, again, this is a tool for saying something, why a model did what it did. So we choose a data point. Here is a person that we print him out. We pass this image through the model, and it says he's a male, he's not smiling, he's not young. Okay, so the arg mode here is PN, that's for pertinent negative. If you look at the paper, all methods have their own parameters, and you can learn them there. So we pass it through, and the first thing it does is load all the classifier models, runs the algorithm, and what it outputs is this image. The pertinent negative, it says he's male, he's smiling, and he's still not young. So what changed here? He is smiling, and the reason why, it added high cheekbones. So the other person was male, not smiling, and not young, because if we would have added high cheekbones, he would have changed classes to smiling. And very quickly, hopefully, let's look at this credit approval tutorial. This is based on the FICO data set that was released last year, or in 2018. So we have different stakeholders here, the data scientist, the loan officer, and the bank customer. If we look at the data scientist, he wants to know why the tool he's developed is doing what it's doing. So we look at the data. The columns here of FICO are the customers, and then the rows are different attributes. And so for the Boolean rules with column generation, because we're making Boolean rules, we need to discretize the data, which is continuous. So now we create these different rules. So here you have external risk estimate, and you can create different rules that say, is it less than or equal to 59, 63, 66, is it greater than 59, and so forth, all binary rules. So we do this to all the features, pass it through the tool, and what it outputs here at the bottom, predict y equals 0 if any of the following rules are satisfied. Otherwise, y equals 1. The rule says external risk estimate less than or equal to 75 and number of satisfactory trades less than or equal to 16. So this is saying if he has bad risk and he made very few satisfactory trades, then predict he's risky. Or if his external risk is even lower than 75. If it's lower than 72, it doesn't matter how many satisfactory trades he made, still predict him risky. And this simple rule gave very good, already a very good accuracy, and that's why they were so surprised actually with this tool. Okay, a different stakeholder, the last one we'll look at, is the loan officer. So the loan officer is the guy who tells you whether or not you get your mortgage, whether you get your loan. And when he does that, if he denies you, he wants to know, well, why did I deny this person? And one way he can do that is say, can I find other people that I've denied, other people in the database that I've denied, and figure out what's similar among them? So again, we have all our import statements, we load the data set. Here we're gonna take one of the samples who was predicted as good. So it's someone I should give the loan to. Okay, so we're gonna run what is called the proto-explainer. So this is a tool for looking for, you feed it an example and it's gonna look through the training set and find other examples similar to that, but similar for different reasons. And so what it outputs is here we ask for 5 new customers, and then we can look at the customers and say, okay, why was the other guy approved? Well, all these other guys approved are very similar, and most of them have no debt. And that's why they're approved. So we're looking for similar customers and getting reasons on why they were classified the same. And we can do that also for people that were not approved. Okay, so in summary, we have this new AIX tool developed last summer. It was released finally. It first included just homegrown tools at IBM, but is expanded somewhat with Lyman Shap, and we hope for more. You can see it on GitHub. You can email me with questions. There's plenty of tutorials. It says 13 notebooks there. And coming up with this is really the result of many people. We have other toolkits within Trusted AI. We have Adversarial Robustness. AI Fairness was released the year before AI Explainability. And I believe Causal Inference is currently in the works. So if there's any questions before everyone goes home for dinner.
Thank you for your excellent talk. Something that became apparent from the Amnist example is that sometimes the permanent positive explanations are, well, somewhat meaningless. For example, it just drew 7s on the big 7 to show that if these pixels were lit, then okay, it was 7. But drawing just 7s on it, it was useless. It didn't actually conform to how the shape we saw would become a 7. So how can you explain the explanations, as it were? See if they're good or just something that the computer, you know.
They're the pertinent positive explanation. We're not asking how it would become a 7 better. That's a different question. It's a specific definition. What is the minimal things that are here that it would still be predicted a 7? It's a different type of information, which sometimes won't be useful. So there, I would say, well, these features, one might say that the other features that are on don't matter. What if that's the model, what's the model is doing? And that's something to just analyze and look at to give you some idea. For other, it depends on the applications also. For the facial ones, sometimes the pertinent positive will highlight specifically the mouth and parts of the skin. So parts of those skin that might be telling of age, for example. But you are right that sometimes it's not as useful, and we saw that the pertinent negatives we found were more useful to humans, at least. We even, it hasn't been published yet for this stuff with the monotonic functions, but we did a user study, very large user study, and one of the things we tested for was what part of the contrastive explanations was most useful to people. And the pertinent negative was more useful on average than the pertinent positives.
Any more questions? So let's thank Ronny. Thank you very much.
Let me just say, oh, sorry.
Please.
For tabular data, the pertinent positives, like with the events for fraudulent, there are applications where the pertinent positive actually will be very useful if you go and look at those examples. Sorry.
So thanks again, Ronny.